Hey guys, last video we talked about arithmetic sequences and series. Today we're going to talk about geometric sequences. We'll hold off on the series until next week because I want to talk a little more in depth about that. It's a lot more complicated than the arithmetic series rather. So a geometric sequence, it is like an arithmetic sequence except the pattern's different. Instead of adding something to get the next term, you are multiplying by something to get the next term. So let's say it was 5, 10, 20, 40, 80, ... So on this one, to get from 5 to 10, you multiply by 2. To get from 10 to 20, you multiply by 2. To get from 20 to 40, times 2, and 40 to 80 times 2. So you're multiplying by the same thing every time. Now to get that 2, if you were to take any two successive terms, so let's say 40 and 20, to get that 2, you would divide them. Or take the ratio. That's why this value is called the common ratio. Is the ratio of two successive terms. And the variable we use for that, just like we use D for the common difference, we use R for the common ratio. So if you're multiplying over and over again, then it's going to be like an exponent. And if you were to plot these points with their corresponding ends being the x values and the terms being the y values, it would follow along an exponential pattern. And an exponential pattern, it's y equals a times b to the x minus 1. But we're going to change the values that we have. Instead of y, we're going to have a sub n. And that a is going to be our first term. Our base is going to be r, and the exponent is going to be n minus 1. This way here, if you plugged in 1, 1 minus 1 is 0, r to the 0 is 1, and a sub 1 times 1 is a sub 1. So when you plug in 1, you get your first term back. And if you want plugged in 2, it'll be a sub 1 times r, which is what would give you your second term. So this is how you would get your explicit definition using this formula. So in this case, a sub n equals 5 times 2 to the n minus 1. You can leave it like this. You do not need to get it so the exponent's just n. You're more than welcome to if you want to write it as, because that's 2 to the n divided by 2, right, as 5 halves times 2 to the n. You can write it like that as well. No one's stopping you, but no one's making you do that. You can leave it in this first form. So that's the explicit definition of a geometric sequence. Now to work with the geometric sequence recursively, let's do that same one. 5, 10, 20, 40. So a sub 1 is 5, and r is still 2. So recursively, you're writing the form. To find your nth term, you're doing something to the previous term. And what you do to your previous term to get your next term is you multiply by 2. If you wrote that as 2 times a sub n minus 1, it says the same thing because multiplication is commutative. They say the same thing. But there's an infinite number of sequences where you're just multiplying by 2 every time. I mean, just the powers of 2, 1, 2, 4, 8, 16, 32, 64, so on and so forth, that would follow this pattern. So you also need to state where you're starting. So you need to state what the pattern is and where your pattern starts. And that's about it for geometric sequences. Have fun.